Welcome back everybody to this sixth episode in the openStars video series. In the first four episodes of this series we reviewed a number of basic properties that characterize stars. And then in the fifth episode we wrapped it all up and looked at the big picture by seeing what happens when we plot a big representative sample of stars up in the HR diagram, where we graph stars up according to two of those properties, their effective temperature and their absolute brightness. In this episode, we're going to be dealing with an extra topic that is different from, but related to, what we've talked about in these first five videos, namely something known as the circumstellar habitable zone of a star. Now, this is something where we can still use gray star 3. When gray star 3 simulates a star, it also simulates its circumstellar habitable zone and displays it over here on the right hand side of its output area. So what is the circumstellar habitable zone of a star? It's also known as the life zone, and that's a self-explanatory term. The circumstellar habitable zone refers to the range of distances that a planet should have from its central host star if the conditions on the surface of that planet are to be just right for supporting life of the sort that we have here on Earth. Now, the location of that zone depends, among other things, on the properties of the central host star. And so this topic is really a natural extension to what we've been talking about in the first five videos in this series. Now, as you may know, this is actually quite a topical subject in the popular media these days. Over the last couple of decades, astronomers have found increasing numbers of planets orbiting other stars, stars other than the Sun. These are known as extrasolar planets or exoplanets, and the pace at which we are discovering them is, if anything, accelerating. Now, many of these planets have been found to be gaseous, like Jupiter or Saturn, but many of them have also been found to have solid surfaces, like Earth. Now, not only that, but currently astronomers are developing techniques to detect chemical signatures from some of these exoplanets. And the way things are proceeding, it likely won't be long before astronomers can start to detect whether or not there are molecules present on exoplanets that are related to biological activity, molecules such as oxygen. So we can calculate where the circumstellar habitable zone lies for any given star, and gray star 3 includes this calculation in its simulation. But how? How can we calculate where the circumstellar habitable zone lies for a given star? To do that, we need to start by making an assumption. And the assumption that we're going to make is that for life to develop on the surface of a planet, the conditions on the surface of that planet need to be ones that allow fresh water to be in its liquid state under 1 Earth atmosphere worth of gas pressure. Now, there's quite a bit going on in that statement, and so we're going to need to unpack that a little bit and draw it out. But before I do that, I just want to address an important question of justification here, because it may seem at first that we're being awfully restricted and maybe a little bit small-minded here in our assumption. That how do we know that life really requires liquid water? Couldn't there be some other very different kind of life out there, different from what we have here, that does not require liquid water? And of course, the answer is that we don't really know that there can't be. And so we're not really saying here that there has to be liquid water in order for there to be life, period. If anything, we're actually turning around the logic here and working it the other way. What we are saying is that if we find a planet out there and the conditions are right for there to be liquid water on its surface, then we know for sure that there's at least one type of life that could develop there, namely the type of life that we have here on Earth. Okay, so this does not rule out the possibility that there could be other kinds of life that can thrive in very different conditions. It's just that we need to restrict ourselves to the type of life for which we can calculate the circumstellar habitable zone. So that's the logic here. Well, let's go back now and unpack the assumption that we're making for conditions to be amenable to supporting life, such as we have here on Earth on the surface of a planet. And what we're saying is that those conditions have to allow fresh water to exist in its liquid state under 1 Earth atmosphere worth of gas pressure bearing down on the surface of that planet. So let's draw that out a little bit and see what's important about it. As you may know, here at sea level on Earth, fresh water freezes at 0 degrees Celsius or centigrade. Or alternately, ice melts into water at 0 degrees, depending on whether we're thinking of the temperature going down or up. And fresh water boils away into steam or water vapor at 100 degrees Celsius. Or equivalently, steam will condense into water at 100 degrees, depending on whether we're thinking of the temperature rising or falling. Now, as you may know, those two temperatures, the freezing and boiling points of water, actually define the Celsius or the centigrade temperature scale. Now, as you may know, those two temperatures, the freezing and boiling points of water, are not absolute universal numbers. They depend on the amount of atmospheric air pressure or gas pressure that's bearing down on the water. So, for example, as you may know, if you live at higher elevation, if you live in a place like Colorado where you're several thousand feet above sea level and the atmospheric pressure is lower, then you have to boil your rice and your pasta for a longer time, right? Because the water is boiling at a lower temperature and things take longer to cook. Now, to take an extreme situation, if the atmospheric gas pressure is 0, i.e. if there is no atmosphere at all, then water cannot exist in a liquid state at any temperature. So if you are on a world with no atmosphere, such as, for example, Earth's moon, then you simply cannot have liquid water, period. If you were standing on the surface of the moon and you opened a container of liquid water, that water could not remain liquid for long. It would have to either freeze or boil away into vapor, depending on the temperature. Now, the other part of this is, why do we stipulate that it has to be fresh water? Well, as you may know, the boiling and freezing temperatures of water also depend on the purity of that water. If that water contains salt, that is, if it has any salinity, then that changes the boiling and freezing temperatures. And in fact, if the water is salty, such as that of Earth's oceans, then that lowers the freezing temperature. As you may have noticed, Earth's oceans remain liquid even when lakes and ponds are frozen. So putting it all together, we are really demanding two things for the surface of a planet if it is to support life. Namely, that that planet have an atmosphere that is bearing down on the surface of that planet with about 1 Earth atmosphere worth of gas pressure, so that water can be liquid at some temperature on the surface of that planet. And in addition, we are demanding that the temperature on the surface be between 0 degrees and 100 degrees Celsius so that the water will be liquid. And part of the assumption that's being made here is that the chemistry that leads to life can't really take place very well in ice or in steam. It has to take place in liquid water. Now, so far we've been thinking about things on the Celsius or the centigrade temperature scale. If you think back to episode 1 in this video series, you may recall that astronomers and physicists prefer to do things on the Kelvin temperature scale, also known as the absolute temperature scale. And if you remember episode 1, you might remember what the conversion is between those two scales. It's actually easy. I'm just going to go and look here for the picture that I showed back in episode 1. To convert between these two temperature scales, it's just a matter of shifting the 0 point by 273 degrees. That if you have a temperature in Celsius, you simply add 273 to it in order to get the temperature in Kelvin. So if we have a temperature of 0 degrees Celsius where water freezes, right here on the scale on the left, that corresponds to 273 Kelvin. And if we're interested in the temperature where water boils, that's not included in this picture, but that's 100 degrees Celsius, so we just add 273. So the boiling temperature is 373 Kelvin. So, to put our conditions for life to occur on the surface of a planet on the Kelvin or absolute temperature scale, what we need is for the surface temperature of that planet to be between 273 and 373 Kelvin. So the next thing for us to spend some time thinking about is what is it that determines the surface temperature of a planet? And the surface temperature of a planet is determined by the balance between the rate at which that planet is being heated and the rate at which it is being cooled. So we need to spend some time thinking about what it is that heats the surface of a planet and what is it that cools the surface of the planet so that we can balance the two. Let's start off by thinking about the heating. An idea you may recall from episodes 1 and 4 in this series is that the light emitted by the central host star here, around which the planet is orbiting, is a form of energy. That light is radiant energy. And so therefore, light will heat any object that it is striking. And so the planet will be heated by the light from its central star. Now the total energy being emitted from the entire surface of that central star, remember, is what we call the star's luminosity. That's something that we talked about in episode 4. But of course this planet is not intercepting the total luminosity from the star. The planet is only intercepting a certain fraction of that luminosity, the fraction that happens to be coming in the direction of the planet. And the fraction of a star's luminosity that's intercepted by an area is what we call the flux. Now, when we talked about flux earlier, back in episode 4, we were thinking about a detector, the fraction of a star's luminosity intercepted by a light detector. In this case, the cross-section of the planet is playing the role of the detector and intercepting flux from its central star. So, the greater the flux intercepted by the planet, the greater the heating rate for that planet. Now, another important idea to remember from episode 4 is that the flux that's intercepted here is going to depend on two things. It's going to depend on the luminosity of the star, and it's going to depend on the distance to the center of the star. The flux is going to be directly proportional to the star's luminosity. All else being equal, if that central star is twice as luminous, the planet will be getting twice as much flux, and the heating rate for that planet will be twice as large. The flux also depends on the distance to the center of the star, but that's an inverse square law, that the flux will depend on the square of the distance to the center of the star. If we were to move the planet so that it's back so that it's twice as far away from the central star, then the flux intercepted by the planet would drop by a quarter, and so would the rate at which the planet is being heated. The next thing for us to think about is what happens to the flux that strikes a planet's surface. And what happens to it depends on the color of the region of the planet's surface that that flux is hitting. Flux that hits a darkly colored area on a planet's surface will get absorbed and will contribute to effectively heating that region of the surface. On the other hand, flux that strikes a lightly colored area of the planet's surface will tend to get reflected back into space, and there will be less heating in that region. Now, this might actually agree with your own experience. If you're out on a hot summer day and you put your hand on a black car, you know that it will feel much hotter than if you put your hand on a white car. That darkly colored objects absorb flux much more effectively and therefore get heated much more effectively by the light that is hitting it. Now, on the Earth, the oceans are relatively dark colored areas that are very effective at absorbing flux from the sun and getting heated. Whereas ice sheets and deserts are more lightly colored areas that tend to reflect flux back into space and are therefore less effectively heated. So the total heating rate for the whole planet is going to depend on the fraction of that planet's surface that is lightly colored and therefore reflects flux back into space and is not very effectively heated. Astronomers use the term albedo for that fraction. Albedo is a Spanish word meaning whiteness, and it is symbolized with a letter A. I'm just going to come over here back to the gray star panel here, and I'll just show you that word. We can find it up here in the input control section. I'm going to come back later and talk about this input control in more detail, but for now there's that term albedo. It's symbolized with the letter capital A, and by definition the albedo is the fraction of a planet's surface that's covered by lightly covered stuff like deserts and ice sheets that reflect flux and are therefore not well heated. So because the albedo is a fraction, its range of values is necessarily between 0 and 1. Now, if we wanted to express the fraction of a planet's surface that's covered by dark colored areas that very effectively absorb flux and are effectively heated, that fraction would be 1 minus the albedo. Now, to just get a little bit of practice with this, if we had a planet whose albedo had a value of 0, let's say, that would be a planet whose surface is totally dark everywhere. The whole surface would be very effective at absorbing flux, and so that planet would have a very large heating rate for a given flux from its host star. On the other hand, if we had a planet whose albedo had a value of 1, that would be a planet whose entire surface is very light colored. So the whole surface would be effective at reflecting flux back into space and not getting heated. So that would be a planet whose heating rate is very low for a given flux from its central star. So the moral of the story here is that the larger a planet's albedo, then all else being equal, the lower the rate at which that planet will be heated, the lower the heating rate, and so therefore the lower the surface temperature. And remember, that's what this is all about. This whole discussion is about understanding a planet's surface temperature. And just to let you know, the value of the albedo here on Earth is 0.3. So what does that mean? That means that here on Earth, about 30% of our surface area is covered by things like ice sheets and deserts, lightly colored regions that reflect flux back into space, flux from the sun, and that are therefore not so effectively heated. And that plays a role in determining the surface temperature here on Earth. Now, in order to appreciate what's going on here, it's important to realize that if the process that we just talked about, heating of a planet by interception of flux from its host star, if that were the only thing going on, then the planet's surface temperature would increase upward without limit until that planet melts or something happens to it. Now, obviously, that's not happening, and so that means that this heating rate that we've been talking about must be balanced by the competing process, namely cooling, that this planet must also be cooling itself off at the same time that it's being heated in order to maintain a stable temperature for its surface. So now it's time for us to turn our attention to this competing process, namely the rate at which a planet is cooling itself off. And here we can actually recycle some important ideas from episode 1 in this video series because the situation is really exactly the same as it is with a star. That like a star, a planet is a dense, opaque object that is hotter than its surroundings, that contains excess heat. After all, as we just saw, that planet is being heated by intercepting flux from its host star. So like all such objects in that situation, like stars, the planet tries to cool itself off by shedding its excess heat, and it does that by emitting thermal radiation or incandescence through its surface, just like we talked about for stars in episode 1. And that process by itself cools the planet. Now you might be saying, but wait a minute, the Earth is not glowing the way a star is. However, if we think back to episode 1, remember one of the things that we saw is that the color of an incandescent object emitting thermal radiation depends on that object's surface temperature. And moreover, we also saw that if that object has a surface temperature greater than 3000 Kelvin, then it will emit incandescent radiation that's visible to the human eye. In the case of Earth, its surface temperature is considerably less than 3000 Kelvin, and so its incandescent radiation is invisible. The Earth is emitting incandescent thermal radiation in the infrared band. In fact, we can see this from space. I found this image at NASA's Earth Observatory website, and this is an image that shows infrared emission from the planet Earth, that in the infrared band, the planet Earth is glowing like a star with infrared radiation. And that emission of incandescent radiation in the infrared band is cooling the Earth off. Now there's an additional important factor that we need to take into account when thinking about the rate at which a planet is being cooled through the emission of this infrared and incandescent radiation. And that additional factor is that a planet like Earth has an insulating blanket wrapped around it that prevents some of that infrared radiation from escaping and cooling us off. And that insulating blanket is our planet's atmosphere. That our atmosphere contains some molecules that are effective at absorbing this infrared incandescent radiation as it tries to escape, and that reduces the cooling rate. So the cooling rate here on Earth is actually less than it would be if our planet did not have an atmosphere at all. In fact, if Earth did not have an atmosphere, the average temperature on our planet would be minus 17 degrees Celsius, given the flux that we're intercepting from the sun and the value of our albedo. So obviously, that's lower than is actually the case. So we are getting a boost in our surface temperature due to this atmospheric insulation effect. And that boost in surface temperature, as you may have already guessed, is what's known as the greenhouse effect. So I'm just going to go to a Wikipedia page here on the greenhouse effect and scroll down just so that we have something to look at here. So you can see some flux being intercepted from the sun, the first process we talked about, the heating process, and then there's the Earth re-radiating heat as incandescent infrared radiation to cool itself off, and there's some of that radiation being blocked by the atmosphere, which reduces this cooling rate. Here on Earth, the size of this temperature boost that we get from our atmospheric greenhouse effect is plus 33 degrees Celsius. So that's what boosts us up from minus 17 degrees up to plus 16 degrees for an average surface temperature. So the moral of the story here is that the larger the greenhouse effect in a planet's atmosphere, then the larger that planet's surface temperature will be, all else being equal, given the same amount of flux being intercepted from the host star and given the value of the planetary albedo. Now, a planet's atmospheric greenhouse effect depends on the chemical composition and the density of its atmosphere. It depends on the concentration of molecules that are effective at absorbing infrared radiation, molecules such as carbon dioxide, methane, and water vapor. Now finally, once again, in order to appreciate what's going on here, it's important to understand that if the only process going on were this cooling process we just talked about, cooling by the emission of thermal incandescent radiation in the infrared band, by itself that would cool our planet off until its surface temperature went all the way down to 0 Kelvin on the absolute temperature scale. That's minus 273 degrees Celsius, remember. Now obviously that's not happening, and the reason why it's not happening is because this cooling is being balanced by the competing process, namely the heating rate that we talked about earlier, due to the interception of flux from the host star. Let's talk a little bit more clearly about exactly how the planet's surface temperature comes into all of this, because after all, that's the main point of this whole discussion, is to determine the planet's surface temperature. We saw that the planet is cooling itself off by emitting thermal incandescent radiation just like stars do, although it is doing it with infrared light rather than visible light. But be that as it may, all of the associated ideas that we had for stars also apply here. For example, the total amount of radiation power being emitted from the whole planet's surface is that planet's luminosity. Now, in the case of a planet like Earth, that luminosity is in the infrared band rather than the visible band, but that's okay, it's still a luminosity. And that total radiation power, that luminosity being emitted by the planet, can be expressed in watts, and that total radiation power wattage is the planet's cooling rate. Now, as we saw in episode 4, an object's luminosity varies as its surface temperature to the fourth power, and that applies here as well. So what that means is that the planet's cooling rate will vary as its surface temperature to the fourth power. So that's interesting because we've been talking about this so far as though the planet's cooling rate helps determine its surface temperature along with the heating rate. And you can think of it that way. And at the same time, though, it's also the case that the planet's surface temperature determines its cooling rate. Now, both of these processes that we've been talking about are going on at the same time. That we have both heating of the planet by interception of flux from the host star, given the planet's distance from the host star and its albedo, and cooling of the planet by the emission of thermal radiation, given that planet's surface temperature and greenhouse effect. Both of those things are going on at the same time. Now, for a stable planet like Earth, the surface temperature remains constant for very long periods of time, for millions of years in the case of Earth, which means that even though heating and cooling are both going on, there is no net heating, which is to say there is also no net cooling. In other words, these two processes are exactly balanced against each other, or in equilibrium, or that these two processes, heating and cooling, are exactly canceling each other out. Now that might seem like an astonishing coincidence at first, that the heating rate would happen to exactly match the cooling rate so that there's no net heating or cooling, but it's actually not a coincidence. Remember, we just saw that the rate of cooling by emission of thermal radiation is determined by the planet's surface temperature. So a better way to think about this is that the planet's surface temperature will naturally settle to whatever value makes the cooling rate exactly equal the heating rate, given the amount of flux being intercepted from the central star and given the planet's albedo and greenhouse effect. And that's important because that means that because it's not a coincidence that this happens, that we can expect that planets out there in general will be in equilibrium with stable surface temperatures. So putting everything all together here, thinking about what's involved in both the heating rate and the cooling rate, let's make a list of all the things that the planet's surface temperature depends on. The planet's surface temperature depends on the luminosity of the central host star that the planet is orbiting. That's a property of the star. It depends on the distance that that planet has from the center of the star, and those two things together, the star's luminosity and its distance from the planet, determine the amount of flux from the host star intercepted by the planet. Then we also have the albedo of the planet, which determines the fraction of that intercepted flux that actually heats the planet. Then we have the greenhouse effect. So that's four things: the luminosity of the host star, the distance of the planet from the host star, the planet's albedo, and the planet's greenhouse effect. And that's it. It's worth noting here what the surface temperature of the planet does not depend on. It does not depend on the size of the planet. That actually cancels out in all of this. And it does not directly depend on the composition of the planet either, except to the extent that the composition might affect the albedo, how light or dark various areas of the planet's surface are. Now, so far we've been talking about all of this in terms of what it is that determines the planet's surface temperature, because that's sort of the natural way to think about it. But if we think about it, in our situation where we're trying to determine the circumstellar habitable zone, we actually need to turn the logic around. Because if you think about it, we actually already know what the surface temperature of our planet has to be. It has to be between 273 and 373 Kelvin, the freezing point and the boiling point of water expressed on the Kelvin temperature scale. That's something that we discussed earlier at the beginning of this episode. So we actually need to turn the logic around and ask, what determines, let me go back to the Gray Star 3 output here, what is it that determines the range of distances that the planet must have from the center of the host star in order for the temperature to be in the right range for life to arise, given all these things: the star's luminosity and the planet's albedo and the planet's greenhouse effect. So we have two target temperatures to think about here: the freezing point of water and the boiling point of water. So we have two distances from the central host star to calculate, and those two distances will tell us what the boundaries are of the circumstellar habitable zone. And those two distances from the central star will tell us how far out the circumstellar habitable zone lies from the central star, and it will also tell us the size or the radial width of the circumstellar habitable zone. So let me just zoom in here on this Gray Star 3 output so we can see things a little bit more clearly. So the first of those two target temperatures that we're going to think about is the boiling point of water. So if we calculate the distance that a planet should have from its central star for its surface temperature to be equal to the boiling point of water, 373 Kelvin, then that distance is known as the steam line, and the steam line is depicted in red in this diagram. And that line defines the inner edge of the circumstellar habitable zone. If a planet is inside its own steam line, then it will be intercepting so much flux from its central star that its surface temperature will be above the boiling point of water, and that planet's entire water supply will be boiled away into steam or water vapor and in the planet's atmosphere. Earth's nearest neighbor closer to the Sun, Venus, is inside its own steam line. Any liquid water that might have once existed on Venus's surface has long since boiled away into water vapor in Venus's atmosphere, where it was subsequently destroyed. So today the surface of Venus is dry. The other target temperature is the freezing point of water, 273 degrees Kelvin, and if we calculate the distance that the planet should have from the central star for its surface temperature to be equal to that temperature, that distance is known as the ice line, and the ice line is depicted in blue in this diagram, and the ice line defines the outer edge of the circumstellar habitable zone. Now notice that the ice line lies further out than the steam line. That stands to reason. The further you go out from the central star, the less flux you're intercepting from that star, and so the lower the surface temperature. So for a planet that's outside of its own ice line, that planet will be intercepting so little flux from the central star that its surface temperature will be below the freezing point, and that planet's entire water supply will be frozen. And Earth's nearest neighbor, further out from the Sun, Mars, is outside its own ice line. that if any liquid water on Mars's surface today would quickly freeze. So the circumstellar habitable zone will lie in between these two lines, the steam line and the ice line, and the habitable zone here is depicted in green. So in that zone, the planet's surface temperature will be between the boiling point and the freezing point of water. In other words, in that zone, the planet's surface temperature will be just right for liquid fresh water under 1 Earth atmosphere worth of gas pressure to exist, and those are the conditions that we said would be ideal for life to arise, similar to what we have here on Earth. So because that zone is the one where the surface temperature of the planet is just right, not too hot as it would be in here, and not too cold as it would be out here, for that reason this zone is sometimes referred to as the Goldilocks zone. So reviewing everything we talked about to get to this point, a planet's circumstellar habitable zone is going to depend on one property of the central star, namely its luminosity. And it's going to depend on two properties of the planet itself, its albedo and its greenhouse effect. So now it's time for us to start doing some experiments with gray star 3 so that we can play with this a little bit and check out various scenarios. But before we do that, I just want to make a few comments about what's going on here in gray star 3's output where it displays the circumstellar habitable zone. Because there's a number of things going on here. First of all, the units of distance that are being used here in order to express how far out the steam lines and ice lines are from the center of the star is the astronomical unit. That's what AU stands for, the astronomical unit. And that's a unit of distance. Now, we could have used units that are more standard in the metric system here, such as meters or kilometers or something, but then these numbers would have come out being very large and not very meaningful. By definition, 1 astronomical unit is Earth's average distance from the center of our own sun. Or another way to think about that is that 1 astronomical unit is the average radius of the Earth's orbit, almost circular orbit, around the center of the sun. And that distance is about 150 million kilometers. So that's about the size of 1 astronomical unit. Now, by expressing the distances to the steam line and the ice line in AU, that makes the numbers much more meaningful, and it also gives us results that we can compare directly to the situation for Earth here in our solar system. That Earth obviously resides within its own circumstellar habitable zone, and that zone is around 1 AU from the Sun in our solar system by definition of the AU. Okay, the other thing that's going on here is that we are using logarithmic scaling, and that's something we've talked about a number of times already in this video series, that the number of pixels out from the center of the star that's being used when drawing the steam line and the ice line is actually being scaled with the log base 10 of the distance from the center of the star in astronomical units. And so remember, what logarithmic scaling does is it compresses larger distances with respect to smaller distances. And so that's going to distort this diagram. It's going to make the distance to the circumstellar habitable zone look small compared to the radius of the star, and it's going to make the circumstellar habitable zone look thinner than it really is, but that's because we're using this logarithmic scaling rather than directly proportional linear scaling. And that's being done because we need to be able to fit the largest situations that we can simulate into the browser window here. So that requires us to use this logarithmic scaling. So let's carry on with our experiments here. So I'm just going to go back up to the top where the control panels are, and I'm just going to zoom out here. Now the situation this time is a little bit different than what we had before, in that now we have two objects whose parameters we have to think about, namely the star and the planet. Now the controls for the parameters of the star, of course, are the ones that are in this top input panel, the one with the green background color. Those are the controls that we've been working with all along in this video series. And in addition, down here in the second input panel, the one with a more yellow background color, these are the parameters controlling the surface conditions of the planet that we've talked about, the greenhouse effect and the albedo. So let's start by experimenting with the object that we are the most familiar with so far, namely the star. And remember, it is the star's luminosity that's going to control where the circumstellar habitable zone is. Now, as always, we want to make sure that we're starting off with our initial primary reference object, the sun. So let me hit reload to make sure that that's where we are. When we reload Graystar, the stellar parameters come up with their solar values, so we're simulating the sun by default. And I'll also let you know, because now it matters, when you reload Graystar, the parameters for the planet come up defaulting to Earth's values for the greenhouse effect and the albedo. So the situation is defaulting for that of the Earth and the Sun. So let's just go down here and do a reality check. It's the luminosity of the star that's going to be important. So let's make sure that our simulation has the luminosity of the sun to start with. That's printed out down here, as you may recall from episode 4. And you can see we're defaulting to a luminosity a little bit less than 1 solar luminosity. Now remember, for various reasons, that's as close as we can get to 1 solar luminosity, but we're going to say that that's close enough for us to work with. And if we go down here to the output panel showing the circumstellar habitable zone, you can see that it's defaulting to a range of distances that straddle 1 astronomical unit, where Earth's orbit is. And so we are defaulting to the situation for Earth's circumstellar habitable zone around the Sun, just as we should be. So that's where we're going to start from. Now, the stellar parameter that directly controls the circumstellar habitable zone is the star's luminosity, but notice or remember that we have no luminosity knob here. That is not one of the things that we can directly adjust. And the reason for that, remember, is because luminosity is not one of the most directly measurable parameters. When we do this kind of simulation of stars, we prefer to control inputs that are most directly measurable, and that does not include luminosity. However, we can indirectly control luminosity by changing the input parameters that affect luminosity. And remember, those are the effective temperature, that the luminosity will go as the effective temperature to the 4th power. And the other parameter that controls luminosity is radius. Luminosity goes as the star's radius squared. Now, we don't have a radius knob either, but remember, for fixed stellar mass, we can control the radius by adjusting the surface gravity. So that's how we're going to proceed. We're going to change the star's luminosity by doing experiments with the effective temperature and surface gravity knobs. So let's start by doing some experiments with effective temperature. So I'm going to grab a hold of this effective temperature knob here, and I'm going to double the effective temperature from the sun's value of 5800 Kelvin. So I want to turn this up to 11,600 Kelvin or so, and probably the best bet is just to type in here to get the exact value I want. Okay, so now let's take this in stages. Let's start off by checking what happens to the star's total luminosity. So I'm going to come down here first and look at the luminosity output, and I'll hit the model button as a little test of what we learned earlier in episode 4. What do we expect to happen to the luminosity if I double the effective temperature? Is it going to go up by a factor of 2? No, it'll go up by a factor of 16, right? I've doubled the effective temperature. Luminosity goes as that temperature to the 4th power, and 2 to the 4th power is 16. So let's go. Here I am hitting the model button. And you can see that the luminosity has gone up to about 14 solar luminosities, but remember we started at a value that was a little bit lower than 1 solar luminosity, so that's about right. That is an increase of a factor of 16. Okay, let's go down and see what's happened to the circumstellar habitable zone. Now before we do that, let's just have some fun and make a prediction. Do we predict that the circumstellar habitable zone will be where it was before at about 1 astronomical unit from the star? Or do we predict that it will have come in closer to the star or moved out further from the star? And I think we should predict that the circumstellar habitable zone will now lie further out from the star because we've made the star more luminous. But let's go down here and check that and see what happened. So there's the circumstellar habitable zone. Now notice first of all, as a little check here, the color of the star is changed. It's now more white in color because we've turned up the effective temperature, so that's what we expect. That has to do with what we talked about in episode 1. And you can see that as predicted, the circumstellar habitable zone has moved out further from the center of the star. Now, it's a little bit hard to tell that just by eyeballing the diagram compared to what we had before. The real way to tell is to look at these printed results for the two lines that border the circumstellar habitable zone, the steam line and the ice line. And you can see that those values are now significantly larger than they were before. That the circumstellar habitable zone has now moved out so that it's spanning the range of distances from about 4 to about 7.5 astronomical units. Okay, now does that make sense? Well, we've made the star much more luminous, 16 times more luminous. If the planet had stayed where it was before at 1 AU, then it would be intercepting much more flux from the star, and its surface temperature would be very high, above the boiling point of water. So what has to happen in this case is the planet needs to move out to a greater distance where it will be intercepting less flux. Remember that the flux goes down as the inverse square of the distance from its central star. And so out here is where it has to move so that it is still intercepting the right amount of flux to keep the temperature in the right range for the planet to be in the habitable zone. So this result makes sense. Now let's go the other way. So let me go back up to the top again to the control panel. Now if I wanted to do this in a very controlled way, I could reload gray star 3 so that I'm defaulting back to the sun's situation again, and come down here and check that I am back to a circumstellar habitable zone that's at about 1 AU from the sun. So there we are, back to the situation for the sun again. Now I'm going to grab that temperature knob and turn it down as far as it will go, to 3500 Kelvin. Okay, so that's not quite half the sun's value, but it is significantly lower than the sun's value of the effective temperature. So again, let me start off here. I'm going to take it in stages. We're trying to affect the luminosity, so let's see what happens. We're back to a value close to 1 solar luminosity. I'll hit the model button, and the luminosity drops to a value a little bit less than 0.12 solar luminosities because we've turned down the effective temperature. So now, before we take a look, what do we think will have happened to the circumstellar habitable zone? Well, this time we would predict that it has moved in closer to the star because we've made that star less luminous. Let's have a look. And again, it might be a bit difficult just to eyeball it from the diagram, but you can see from these printed results here that indeed the circumstellar habitable zone has now moved in closer to the star, that it's now spanning the range of distances from a little more than a third of an astronomical unit to about 0.7 astronomical units. And of course, again, that makes sense. We've made the central star less luminous. If the planet had stayed out here at 1 AU, it would be intercepting too little flux, and its surface temperature would be lower than the freezing point of water. So in this situation, the planet has to huddle around closer to its less luminous, cooler central star in order to have a surface temperature that is in the right range for the life zone. Now remember that the central star's luminosity also depends on its radius, not just its effective temperature. And I do want to do just one experiment where we adjust the central star's radius and see what happens. In fact, what I'm going to do is I'm going to leave the surface temperature here at 3500 Kelvin. So I'm going to leave that alone. So we still have a nice red star, but I'm going to turn up the radius, and remember I'm going to do that via the surface gravity. So I'm going to take the surface gravity knob and turn it down as far as it will go, and at a temperature of 3500 Kelvin it will let me turn that value all the way down to 1.5. The surface gravity expressed as log g, so that's a much lower surface gravity than the Sun. And if you followed episode 3 in this video series, you know what's going to happen to the radius. We're squeezing the star with a much lower force of gravity, so the star can puff up more and occupy a larger volume, and it will have a larger radius. Right now we're still at the Sun's value of 1 solar radius, about. Let me hit the model button, and you can see that the radius has gone up to almost 30 solar radii. What we've done here is we've turned the surface gravity down actually by a factor of 1,000, from log g 4.5 to log g 1.5. And that gives us a much bigger star. Okay, and you can also see the effect on the star's luminosity, that the star's luminosity is now almost 120 solar luminosities. Luminosity goes with a square of the radius. So what will that do to our life zone? Well, once again, with a more luminous central star, we can predict that the life zone will move outwards from the Earth's value of 1 astronomical unit, because we now are modeling a much more luminous star than the Sun. And indeed, we can see what's happened, that the life zone now spans the range of distances going from about 11 astronomical units to about 22 astronomical units. Okay, so we now have a nice big red giant star in here. And remember, actually from episode 5, when we were talking about the Hertzsprung-Russell diagram, astronomers have found stars like this. Stars with very low surface temperatures that are red and that are very large, namely the red giant stars. And you can see that around a red giant star, the circumstellar habitable zone lies quite far out. That's because, being large, this star has a large luminosity despite its low effective temperature. So the planet has to move outwards in order to intercept the right amount of flux to keep its surface temperature in the right range for the habitable zone. Now, I should say that this situation that we've just simulated is not really one where anyone would expect to find life in any case. That for a star to reach the point in its life where it becomes a red giant star, it already has to have gone through some earlier stages where it was less luminous. And so at this point, if you have a star that's a red giant, a lot of things have already changed around that star. A red giant is not a very long-lived stage of a star's life, so this isn't really in a situation in which we would expect to find life on any planet anyway, but nevertheless we can still do the simulation and see where the life zone is. So now the next set of experiments that we want to do are ones where we adjust the planet's parameters and see what happens to the circumstellar habitable zone. So, in the spirit of doing carefully controlled experiments, we're going to want to fix the properties of the central star. So I'm just going to hit reload here so that we're defaulting back to the Sun for the central star. And throughout these experiments, we're just going to leave that alone so that the central star is always fixed to being like the Sun. So we can check down here that we're back to the Sun's radius and the Sun's luminosity, or at least as close as we can get here with gray star 3. Now, when gray star 3 first loads, the parameters for the planet default to values that will give us the right result for the Earth's circumstellar habitable zone. Okay, values that will give us a circumstellar habitable zone that straddles 1 astronomical unit, where the Earth is. So coming back to this control panel where we have the planetary input parameters, you can see that there is the albedo being set to a value of 0.3. That's the value that Earth has. And the value of the greenhouse effect here, the temperature boost that we get for the planet's surface temperature, it's being set by default to a value that's actually somewhat lower than the Earth's real greenhouse effect temperature boost. And that is being done just to force gray star 3 to give the right result for the Earth's circumstellar habitable zone. That's just compensating for the fact that gray star 3's simulation isn't really as realistic as a research quality simulation would be. So those are the values that we're going to be starting from. So I'm going to start by adjusting the greenhouse effect. So remember what that is. That's a boost to the surface temperature of the planet. So that's a temperature boost in Kelvin, and it is the surface temperature of the planet that we're boosting here, not the temperature of the star. So I'm going to grab that and I'm going to double it from 20 Kelvin to 40 Kelvin. Okay, so this is a temperature boost due to the insulating effect of the planet's atmosphere, and I'm doubling that so that the surface temperature of the planet will be 40 Kelvin hotter than it otherwise would be given how much flux the planet is intercepting from its star, instead of 20 Kelvin hotter. So let's go down and see what that does to the circumstellar habitable zone. So I've hit the model button here, so it's now just recalculated the circumstellar habitable zone. But before we take a look, maybe we can make a prediction. What do we think is going to happen to the circumstellar habitable zone if we increase the greenhouse effect significantly? And you might predict that the circumstellar habitable zone is going to move outwards in order to lower the planet's surface temperature again. But let's go down and see what's happened here. And you can see that our prediction is correct. The circumstellar habitable zone has now moved outwards a little bit. Its inner edge, the steam line, now lies out at 1.1 astronomical units. So that's out beyond the Earth's distance from the Sun as it currently is. Okay, so the circumstellar habitable zone now spans the range of distances from 1.1 to a little over 2.2 astronomical units. And that makes sense. By boosting the greenhouse effect, we've increased the planet's surface temperature. So the planet has to compensate by moving out a little bit from the central star so that it intercepts less flux from the star, and the surface temperature goes down again to be within the right range for the life zone. Now, of course, we don't have the option of doing this in real life. In real life, if Earth's greenhouse effect starts to increase and raise the planet's surface temperature, we don't have the option of actually moving Earth further from the Sun in order to compensate. But we can do it in this simulation. Okay, so let's go back, and I'm going to hit reload again so that we are defaulting to the planetary parameters for Earth's circumstellar habitable zone again. So we're back to a greenhouse boost of 20 Kelvin. Let's just come down here and check. We are back to a habitable zone that straddles 1 astronomical unit again. Okay, and this time what I'm going to do is I'm going to adjust the albedo. So that's at 0.3. I'm going to grab a hold of that and I'm going to double it to 0.6. So now we are simulating a planet where 60% of the surface is covered with ice sheets or deserts or material that's nice and shiny and reflective and reflects the heating flux back into space instead of absorbing it. So I'm going to come down here and hit the model button. And before we look at the life zone, we can make a prediction again. We are now reflecting much more of the heating flux back into space instead of absorbing it. And so we can predict that the circumstellar habitable zone will have to move inwards to compensate. But let's go down here and see what's happened. And indeed, you can see that the habitable zone has moved inwards. Its inner edge has moved inwards from being a little bit less than 1 astronomical unit to being more like 0.75 astronomical units, and the outer edge has moved in as well to being just a little bit less than 1.5 astronomical units. So again, that makes sense. With a larger albedo, we are reflecting more of the heating flux instead of absorbing it and letting it heat us. So the planet has to compensate by moving in closer to its central star to raise the surface temperature again to keep it in the values for the life zone. So note that the location of the circumstellar habitable zone does depend on all of these properties that we just experimented with. It depends on the effective temperature of the central star, the surface gravity, and thus the radius of the central star, and it also depends on the greenhouse effect and on the planet's albedo. So let me finish up as always by suggesting a pedagogical activity for teachers. And this pedagogical activity is one that's really going to focus exclusively on the parameters of the planet rather than the star. So this is a pedagogical activity that could actually be appropriate for a unit on environmental science as well as a unit on astronomy. So what I'm going to do here is I'm just going to go back up to the top and hit reload here. So we're defaulting back to the parameters for the sun and the earth, in particular for the earth here. Now part one of the activity, if we come down here to the output for the circumstellar habitable zone, you can see that the circumstellar habitable zone is not centered on Earth's distance from the Sun. Remember, Earth's distance from the Sun is 1 astronomical unit, and the circumstellar habitable zone here is going from just a little bit less than 1 to quite a bit more than 1. So the circumstellar habitable zone is not centered on Earth's distance from the Sun. Earth is actually closer to the inside edge of its habitable zone, the steam line, than it is to the outside edge of it. And that's actually a realistic result, that when people model this situation with more realistic research codes, they find the same thing, that Earth is closer to the inner edge of its habitable zone than to the outer edge. It's not centered in its habitable zone. So part one of this activity would be for students to do some experiments with Graystar, adjusting the greenhouse effect. As they adjust the greenhouse effect, then of course the habitable zone will move in and out, as we've just seen. Can students find a value for the input greenhouse effect that will center the circumstellar habitable zone on Earth's distance from the Sun? In other words, center the habitable zone on a value of 1 astronomical unit. Okay, in other words, find a value of the greenhouse effect that will put 1 astronomical unit halfway between the steam line and the ice line. Because of course the Earth's distance from the Sun of 1 astronomical unit, that's not negotiable. We cannot change that. What would the value of the greenhouse effect have to be for the ice line and the steam line to be equally distant from 1 astronomical unit on either side? Now the students probably can't center the habitable zone on Earth's distance from the Sun exactly, but they can at least do it approximately. So that's part one of the activity. Part two of the activity is that having centered the habitable zone on Earth's distance from the Sun of 1 astronomical unit, what would be involved in keeping the habitable zone there as the greenhouse effect changes? So part two of the activity is a bit more elaborate. What students would do is they would experiment with different input values of the greenhouse effect, varying it over its entire range, maybe in equal increments of 10 degrees or something. And of course, for each value of this input greenhouse effect, that will move the circumstellar habitable zone in or out compared to its default value. Then the activity would be, for each input value of the greenhouse effect, can the students find a value of the albedo that will keep the circumstellar habitable zone centered on 1 astronomical unit? Okay, so the albedo value will also move the circumstellar habitable zone. In other words, can students find a way to use albedo to compensate for the effect of the greenhouse effect to keep the circumstellar habitable zone fixed, centered on the Earth's distance from the Sun? And that will take some trial and error experimentation. Now, students may only be able to do this approximately, but they can produce a data set. For each greenhouse effect value that they input, they will get a resulting albedo that keeps the circumstellar habitable zone fixed, centered at 1 AU. Now, they may not be able to find a value for the albedo that will do this for the full range of the greenhouse effect. In fact, they probably won't, but they should be able to find values of albedo that do it for a significant range of the greenhouse effect values. Then they can take this data set of albedo values corresponding to input greenhouse effect values, and they could make a graph of albedo versus greenhouse effect that would show what the relationship is between those two things for a circumstellar habitable zone fixed centered on one astronomical unit. So that's today's pedagogical activity. Let me finish off as always by going upstairs here in the directory structure and just reminding everybody of the main Graystar 3 page, that on this page teachers and students and anyone interested can find links to various resources such as a community forum for sharing ideas and suggestions for lesson plans and projects and so forth incorporating Graystar 3. As always, if you're going to use this, you may wish to download your own local installation. So there's a file there that you can use to do that. If you're not sure what to do, then maybe your IT professional at your school or your university can help you. Okay, so that actually brings us to the end of the first series of videos. We've now done everything. We're at the end of the first 6 videos. Thank you for watching. There may be a future series of videos coming where, if I go back to the Graystar 3 page here, where we talk much more about this thing, about the star's spectrum, and in particular what can be learned by looking at these individual dark line spectral features that we talked a little bit about in episode 3. So that may be coming someday, but for now, thank you for watching, and good luck with your teaching and learning about stars and planets.